In this module, we consider in detail the layout and components which comprise the steering system and front axle on the Olympian. First of all, the steering box and steering wheel linkage. The upper section is a one-piece unit splined to the steering wheel, and the lower section, which connects to the steering box, has upper and lower universal joints and a slipper joint to facilitate adjustment of the steering wheel height and angle. The steering box is located here, secured by 4 bolts which are wired in pairs for additional security. Steering movement is transmitted to the stub axle steering arms via the steering box drop arm by a drag link. The front ball joint on the drag link is screwed to the drag link tube where it is clamped. This allows the linkage and the steering to be adjusted should it be required. Should it become worn, the ball joint can also be replaced. To complete the steering linkage, the drag link is connected to a central relay lever on the axle, which operates through 2 half track rods to the right and left-hand stub axles. Each of the 2 track rods are provided with left and right-hand threads to allow for adjustment of the steering track should it be necessary. It should be noted at this stage that the 3-axle Olympian has a dual relay lever to give increased lock angles. The front axle is of an I-section profile in forged steel. The outer ends are machined to accommodate tapered stub axle kingpins. The axle beam is attached to taper leaf springs by 4 bolts and a lower clamp plate. In the case of the 3-axle Olympian, the intermediate axle is located in a similar manner. However, because the axle is self-steering, it does not have any steering linkage other than the half-track rods and central relay arm. Finally, we consider the stub axle, which on the Olympian has a tapered kingpin locked into position by a castellated nut, which reacts through the inner track of the upper taper roller bearing and the adjusting spacer onto the axle beam. The stub axle has a plastic bush at the bottom and a taper roller bearing at the top to support the vehicle load. The running clearance of this bearing is also adjustable by shims between the spacer and bearing. Maintenance, steering linkages and front axle. A check on the security and condition of the steering system is of the utmost importance from a safety point of view. The bolts for the steering box must be checked for looseness and signs of movement. The steering box drop arm nut must also be secure and properly locked into the shaft detent. The steering box hoses and connections must also be free of leaks. It's important to note that when checking for leaks, the engine must be running with the steering being rocked from side to side. This ensures that sufficient pressure is being developed within the system. Refer to the PSV Tester's Manual for confirmation of what constitutes a fluid or oil leak. Steering universal joints and slipper shaft splines should be checked for security and wear by rocking the steering back and forth. It is recommended that this be done at the same time when checking for leaks. The maximum permitted play in the slipper joint is 1.5 millimeters measured at the circumference of the shafts. The steering column mountings and steering wheel must also be checked for condition of security. Any loose bolts must be tightened. All ball joints should be checked for wear and excessive movement. To do this, compress the joint axially, like this, using suitable poly or gland nut pliers. The movement should be checked and recorded. The movement when compressed should not exceed 2 millimeters. A dial indicator or vernier caliper can be used to confirm the exact movement. If steering joints do not comply, they must be replaced. When carrying out these checks, also make sure that the track rod and drag link ball joint ends articulate equally. If not, reset the ball joints. Whilst in this area, carefully inspect all rubber gaiters for damage. Remember that the smallest of holes will allow abrasive material into the ball joint, and although it may initially be serviceable, rapid deterioration will normally result. In situations like this, the ball joint should be replaced. The stub axle must then be checked for security and bearing wear. With the vehicle wheels on the ground, check the clearance between the top of the axle beam and the underside of the stub axle, as seen here. Providing the clearance is between 0.05 and 0.15 millimeters, the setting is correct. If it's outside these limits, adjust the shim thickness between this sleeve and the inner track of the taper roller bearing. To complete the inspection of the stub axle, a check should be made on the radial play in the kingpin bush. To do this, the front wheels must be raised off the ground. Apply the foot brake and keep it pressed using a pedal jack or blocker. This is necessary to eliminate the effect of hub bearing end float. Then place a set square in contact with the tyre wall. Next, lever the bottom of the wheel out and reposition the set square, ensuring that it's making good contact with the tyre. With the wheel bar positioned at the top of the wheel, lever the wheel inwards, then measure and record the clearance between the tyre wall and the set square. From this conversion graph, which is contained in the workshop manual, the movement of the tyre wall can be converted into bush clearance. The maximum permitted clearance between the bush and the kingpin is 2 millimeters. Finally, check for roughness in the steering bearing universal joints and ball joints. To do this, the front wheels are raised off the ground with suitable axle stands placed under the axle. Note that this test must be done with the engine stationary, as the power steering could mask and absorb some of the roughness that may be in the system. With the aid of an assistant to turn the steering, check for any vibrations or tightness in the linkage as the steering sweeps from lock to lock. Any defective components should be replaced. With all these checks complete, the steering components can now receive the relevant lubrication service. This involves the grease lubrication of the stub axle top and bottom bearings, slipper shaft splines, and each of the steering universal joints, using either a hand or power greaser. The grease specification used must be lithium-based with EP additives and consistency NLGI number 2. Power-assisted steering. In this section, we consider the general specifications, basic function, routine maintenance, and external adjustments on the power-assisted steering system used on the Olympian. We begin by looking at the specification and the basic function of the system. The Olympian features the fully integral chassis-mounted ZF8097 power-assisted steering unit on the 2-axle Olympian, with a heavy-duty 8098 variant on the 3-axle. In principle, the operation of both units is the same. The main housing of the steering unit itself contains an operating piston which slides within the integral power cylinder. One of the faces of the piston is machined in the form of a rack to which the sector shaft is geared. Mechanical movement from the steering spindle is by worm screw, which is engaged into the power piston by recirculating balls. The unit also contains a torsion bar to give control and feel to the steering. This end of the torsion bar is connected to the worm, and the other to the input spindle from the steering wheel. In this area, a rotary valve is located to distribute the oil from the hydraulic pump to operate the power piston. The torsion bar and steering spindle are linked to the worm by this drive pin, which is in an elongated slot in the worm. When steering effort is applied to the steering wheel, the spindle is able to rotate and operate the rotary valve by loading the torsion bar. This small angular movement can take place without moving the main steering because of the elongated slot in the worm. From this diagram, the valve action can be seen. Here, for example, is the valve in the neutral position, with the supply and delivery ports identified. When the steering is turned, the valve moves to this position, and oil is directed to move the operating piston to the right or left, depending on the steering direction required. In this example, the steering is being moved to the right. The displaced oil from this side of the piston is returned to the reservoir via the rotary valve. This movement is transferred to the sector shaft drop arm and finally to the steering linkage. In the event of failure anywhere in the hydraulic system, the steering gear will still operate mechanically via the drive pin. Moving to the hydraulic system. The hydraulic system on the Olympian operates in a dual role, supplying oil not only to provide power-assisted steering, but also to operate a hydraulically driven fan for engine cooling. Although this training module is intended to cover the steering, we will in this instance consider the fan operation because of the integrated operation. An engine-driven hydraulic pump draws oil from a reservoir via a strainer. The oil is then pumped through a small reservoir which damps out oil pulsations from the pump. From here, the oil continues on to a line-mounted oil filter and then to a switching valve. This unit is responsible for distributing the oil supply to the hydraulic fan and the power steering unit. It also controls the flow rate and maximum operating pressures for both systems. The unit is also designed to give priority oil flow to the power steering at all times. From the switching valve, the oil passes to the steering box before returning to the reservoir. The maximum operating pressure when the steering is under full load is approximately 130 bar, which, as mentioned earlier, is controlled by a pressure relief valve within the switching valve. Moving now to the hydraulic fan. Providing the coolant temperature is below 88 degrees centigrade, the oil supply from the pump passes through a thermostatic valve which holds the switching valve in the closed position, and the cooling fan is not operative. However, a quantity of oil does pass to the fan motor, sufficient in most cases to rotate it at low speed, and then the oil returns to the reservoir. When the engine coolant temperature reaches 88 degrees centigrade, the thermostatic valve progressively shuts the oil supply to the switching valve. The switching valve now allows oil pressure through to the fan motor, driving it at high speed. The fan speed does vary depending on engine speed and oil supply pressure. For example, at maximum engine speed, the fan speed is approximately 2,500 RPM with an oil pressure of approximately 84 bar. To complete in this area, let's for reference purposes locate and identify the units concerned. The hydraulic reservoir is mounted here within the engine compartment with a sight glass for the oil level. The hydraulic pump is mounted on the engine timing cover, the location of which will vary depending on the engine specification. Here, for example, is the installation on the Volvo engine, and here on the Cummins. It should be noted that the oil output from the pump passes through a small reservoir, the purpose of which is to damp down the hydraulic pulsations from the pump to reduce hydraulic noise. From here it then passes to a line-mounted filter and on to the switching valve, fan motor and power steering unit. Maintenance and running adjustments. Contained in the main operating piston are two unloader valves which are set to come into operation to reduce the system operating pressure just prior to the steering stub axles reaching the lock stop on full right or left-hand lock. From this diagram, the principle can be seen. This is the right-hand valve and this the left. If the steering is moved to the right-hand valve strikes the adjusting screw, which lifts the valve from its seat, allowing the high pressure from this side of the piston to pass to the other side, which is connected to the return to the reservoir. When the valve is open, the operating pressure is reduced considerably to prevent a steering overload condition. The point at which these valves unload on each lock can be adjusted by these screws at the top and bottom of the steering box. The upper adjustment controls the right-hand lock, and the one at the bottom, the left-hand lock. Unloader valve checking and adjusting. Whilst the setting of these valves is not included in any part of the standard maintenance plan, they do, however, require to be checked and, if necessary, adjusted whenever the steering linkage has been altered or where the steering box has been replaced, or as part of the fault diagnosis of the steering or front suspension. In order to undertake this type of work, certain specialized equipment will be required. In this program, however, the procedure will be undertaken using only Volvo special tools and test gauges. The tools involved include this dual-gauge pressure test instrument, which is fitted with 2 hoses, each with self-sealing connectors. The hoses are identified as inlet and outlet. However, for the purposes of this particular procedure, only the inlet hose will be used. The instrument is also fitted with a shut-off valve controlled with this lever. When the lever is in the closed position, it shuts off the flow to the outlet hose. This lever, again for the purposes of this procedure, should be set in the closed position. This elbow adapter is also used to connect the test instrument into the steering pump pressure line. Finally, there is this special spacer sleeve, which is used to cover the left and right-hand rear lock-stop bolt when checking and adjusting the left and right-hand unloader valves. In order to check and adjust the unloader valves on the steering box, the bus must first be raised so that the front wheels are cleared of the ground and supported on suitable stands placed under the axle. Remove the protective cover from the pressure line connector and fit the elbow adapter. Connect the inlet hose of the test instrument to the adapter. Finally, place the 5mm spacer sleeve over the left-hand rear lock-stop bolt. Before proceeding, ensure the park brake is on, the gearbox is in neutral, the road wheels are chocked and exhaust extraction connected. Start the engine and adjust to run at low idle. Unloader valve checking and adjusting. Turn the steering wheel to the left until the lock-stop bolt touches the spacer sleeve. At this point, a slight pressure surge should be observed on the test instrument gauges. Pull hard on the steering wheel for no more than 5 seconds and read off the pressure, which should be between 30 and 40 bar. If the pressure is incorrect, adjust the lower unloader valve adjuster screw while holding the steering hard against the lock stop. Note again that the steering should not be held hard against the stop for any more than 5 seconds at a time. The screw should be turned anti-clockwise to increase the pressure and clockwise to decrease. When the valve is adjusted to the correct unloading pressure, tighten the lock nut. Turn the steering off the left-hand lock and remove the 5mm spacer from the stop bolt. And refit to the right-hand stop bolt. Then continue turning until the right-hand stop bolt touches the spacer and repeat the check for right-hand lock. If you wish to check the steering track, first set the steering in the straight ahead position. Insert a peg into the centralizing hole in the relay lever. Next, check that the wheels are parallel to the chassis by using a gauge at the front and the rear of the wheels. The gap should be equal. If not, lengthen or shorten the half-track rods to correct this situation. However, after each adjustment, the vehicle should be rolled forward 1 complete turn of the road wheels to eliminate tire friction buildup. The same procedure should be used on the other wheel. Unless this procedure is followed, the steering lock angles will be incorrect. When complete, the overall track on the vehicle can be measured using conventional equipment set to 0. Should any adjustment be needed, adjust each track rod equally. The same procedure should be used on the intermediate axle on the 3-axle Olympian. It should be noted that if the wheels are out of parallel on the initial check, the unloader valves on the steering box will be required to be reset. Upon completion, do not forget to remove the centralizing peg on the relay lever. On the 3-axle Olympian, the intermediate axle is a self-steering unit with limited lock angles. Steering damper units are fitted between the steering stub axles and axle beam to stabilize wheel movement under adverse road conditions. When the vehicle is reversed, the steering track rods are locked in the straight-ahead position by these 2 air cylinders. Operation of these is triggered automatically when reverse gear is selected. The basic setting procedure for the steering linkage using the centralizing pin is identical to the front axle with the exception of reversing cylinders. The push rods on the air cylinders are adjustable, and in order to check the setting, fit the centralizing pin in the relay lever. With the cylinders extended, remove this seal on the actuator, release the lock nut and screw in the central screw. This should be done on both units with the cylinders still extended. Screw out the adjuster screws until contact is made with the relay. Then screw out a further one flat and tighten the lock nut. This same exercise should be carried out on the other cylinder. Make sure that the seals are replaced. Again, on completion, don't forget to remove the centralizing pin. From a maintenance point of view, always check for air leakage from the cylinder vent holes when they're engaged. Also, make note lubrication points are also provided on the push rods. Power steering maintenance. From the maintenance point of view, there are two filters in the hydraulic system. First, there is a strainer in the base of the reservoir. After draining the system, access can be gained by first disconnecting the suction pipe and releasing these retaining nuts. Providing the filter is only lightly contaminated, it's in order to clean it. When replacing, make sure that the filter is securely tightened to the mounting plate. Positioned at the front of the vehicle is a line-mounted filter, access to which can be gained by releasing this filter bowl. The filter in this case cannot be cleaned and should always be replaced. However, due to the operating temperatures and pressures of the system, always fit recommended parts. It is important to remember that due to the close running tolerances of the hydraulic pump, switching valve, steering box and fan motor, any dirt ingress into the system can cause failure or intermittent faults. Therefore, always clean the area around the unit prior to removal and maintain a high level of cleanliness. To refill the system, top up the reservoir to the maximum mark. Start the engine and allow to idle for 2 to 3 minutes, topping up the reservoir as required. Next, move the steering from lock to lock. This procedure will enable the system to purge any air present in the circuit, and then finally top up the reservoir to the maximum level. In this module, we'll be looking at the procedures involved in removing, replacing and adjusting the front and rear hubs. First, let's consider the front hub. Before proceeding with the removal, let's briefly look at the hub structure and its component parts. The hub is supported by an inner and outer taper roller bearing, which is normally a sliding fit on the stub axle. Between the bearings are two spacers with a spring washer, the purpose of which is twofold. When the outer retaining nut is tightened to a specified torque, the inner tracks of both bearings are clamped to avoid any possible rotation on the stub axle, and at the same time the specified hub end float is obtained. A safety washer is fitted between the outer bearing and the hub retaining nut, which enables the bearing to slide against it in the event of bearing failure. The washer is located on a polygon recess on the stub axle to stop any rotation. The hub has an oil seal and is lubricated by oil with a level indicator in the cap. If you wish to check the hub end float, the vehicle must first be jacked and supported on suitable stands. Remove the road wheel and brake drum. If the drum is tight, extractor holes are available in the drum. There may also be instances where the brake shoes may have to be de-adjusted to clear the brake drum. This can be achieved by this adjuster on the brake backplate. The adjuster should first be pushed in like this to release the locking mechanism and engage the adjuster mechanism and rotate it in the same direction as wheel rotation. Make a note of how many turns are made so that the brake adjustment can be reset when the drum is reassembled. If this grommet is now removed from the center of the hub cap, it enables the probe of a dial gauge indicator to be inserted onto the end of the stub axle, and with the base on the hub face, end float can be measured, which should, if correct, be 0.04 to 0.12 millimeters. If the end float is incorrect or the hub required to be removed for inspection, the following procedure should be followed. Unscrew the hub cap. Remove the lock ring and lock washer. Remove the hub nut and safety washer. The outer bearing can now be removed. At this stage, you should be able to slide the hub off the stub axle. However, if it is tight, a puller is available if required. The oil seal wear ring is replaceable if worn. If the hub is completely stripped down, ensure that the spring washer, which is retained in the spacer by a spring clip, is fitted with the curved section facing the outer bearing, as seen here, exaggerated on this diagram. Prior to assembly, lightly grease the oil seal running surfaces to avoid damage to the seal during initial running. Oil the inner and outer bearings, washers and stub threads. Assemble the hub onto the stub axle. Enter the spacer, bearing and safety washer. Next, fit the hub nut and tighten to a torque of 450 Newton meters. At the same time, rotating the hub backwards and forwards to ensure correct bearing location. To continue, back off the hub nut by 60 degrees, which is the equivalent of one flat on the nut. With the dial gauge indicator in position, read off the end float, which should be 0.04 to 0.12 millimeters. It's important that the hub has end float to the specified figures, otherwise premature hub bearing failure will result. Therefore, if there is insufficient clearance, the hub nut should be released slightly to achieve this. When complete, fit the lock washer. In order that the hub nut can be locked in any desired position, the lock washer tongue and nut slots are out of pitch. Therefore, it may be necessary to rotate the washer until the correct relationship is found, allowing the lock plate to locate correctly. With the lock plate in position, fit the lock ring. Before fitting the hubcap, check the condition of the O-ring and replace if necessary. Tighten the hubcap to a torque of 250 Newton meters. To complete the exercise, refill the hub with oil to the level indicator in the hubcap. Moving now to the rear hub. The rear hub is again supported on two taper roller bearings with bearing adjustment by means of the hub nut. The lubrication is by grease. The main hub seal is located here with an oil collector which directs any leakage through drillings in the front face of the hub to avoid contamination of the brake linings. A second seal, located on the hub lock nut, seals against the drive shaft, which prevents any oil transfer from the rear axle differential unit. To remove the hub, first chock the road wheels, release the park brake. Using suitable jacks and support stands, jack the vehicle up and remove the road wheels. Next, remove the drum, using the same method as the front by de-adjusting the brake shoes and using jacking bolts if necessary. Now, remove the drive shaft. Then, the hub lock nut. Finally, removing the lock washer and the main hub retaining nut. The hub in most instances can be slid off the axle tube. Before replacing the hub again, lubricate the oil seal running surfaces and repack the roller bearings with grease, ensuring that it has penetrated between the rollers. The main hub chambers should also be packed with grease as per this example. The hub can now be lifted into place and the outer bearing pushed into position. Next, refit and tighten the adjuster nut. Again, rotating the hub to ensure the bearings have seated correctly. Release the adjuster nut to give an end float of 0.25 millimeters. At this stage, fit the lock plate and lock nut and tighten to 300 Newton meters. You will now find, if the end float is rechecked, that it will have reduced from the original setting due to the lock nut taking up clearance in the adjuster nut threads. If correct, the clearance should be 0.04 to 0.12 millimeters. If this is not the case, slacken the lock nut and reset the adjuster nut until the desired end float is obtained with the lock nut tightened. To complete the exercise, replace the drive shaft and brake drum. It should be remembered that if the air pressure on the vehicle drops and the spring brake progressively applies the brakes, this may cause damage to the brake mechanism. Therefore, unless the air pressure can be maintained, the spring brake should be wound off before the drum is removed and reset on completion. This now completes the training module on steering and hubs on the Volvo Olympian, and we hope you find the material in this program helpful.